A crew member drifts through a station module with one hand on a rail and both feet doing nothing. The body looks calm. The hips and spine look unburdened. That calm is the deception. The skeleton is already losing its reason to stay strong. Zero gravity removes the mechanical load that weight-bearing bone needs to hold its density. Without daily pressure through the hips, spine, and femur, the remodeling balance shifts. Osteoclasts break bone down, osteoblasts fall behind, and density drops month by month. The danger is not unusual sleep habits in orbit. The danger is every hour the skeleton spends where weight has stopped asking anything of it. By the end of this video, you will understand how that remodeling imbalance develops, what the density numbers mean for a crew arriving at Mars, and why the countermeasures that protect a 6-month station stay may not be enough for a multi-year transit. If you enjoy exploring questions like this with us, subscribing helps others find them too. Sharing the video helps even more. Let's begin. That handrail is the clue. Gripping it is not the danger. The clue is what the crew members' feet are not doing. There is no floor pressing back under them, no downward push through the legs, and no quiet reminder from the world that the skeleton is carrying something. On Earth, that reminder never stops. Standing in a kitchen sends load through the hips. Stepping off a curb sends it through the femur. Even catching yourself after a stumble, that small unconscious correction drives force through the lower spine. The signal is mechanical, not poetic. Keep structure here, maintain this region. The work keeps arriving, so the bone stays ready. In orbit, the same body drifts on a hand push. The floor has been replaced by a grip. The downward demand has been replaced by almost nothing. That can look like relief. For the crew member, it may even feel like it, but bone is not reading feelings. It is reading load, and load has gone quiet. That is what the peaceful image leaves out. The skeleton is not under attack. It is being unloaded, and unloading, because it asks nothing visible of the body, is easier to miss than a dramatic injury would be. The sleep idea is worth correcting here carefully. Sleep in an unusual cabin is not the mechanism. A person can sleep normally in orbit and still spend every waking hour inside an environment that asks less of the skeleton than Earth ever did. Rest is not the hazard. The deeper risk is the continuous absence of the signal that gives weight-bearing bone its instructions. The regions that matter are specific. Hips, pelvis, spine, and the long bones of the lower limbs carry the most repetitive load on Earth. They push, stabilize, and absorb. They are also what a crew member needs when a mission stops floating and starts requiring physical work. Stepping out of a hatch, steadying against a surface while carrying something heavy, getting up from a fall a long way from a hospital. NASA's public risk documentation gives numbers to what the biology suggests. Weight-bearing bones can lose measurable density during months in microgravity. The concern reaches fracture susceptibility and a pattern that can resemble premature osteoporosis. Its origin is different, so the language has to stay careful. Outcomes depend on the person and the mission length. They also depend on whether countermeasures are working. A managed risk is not a solved one. The measurement exists because the change is real enough to plan around. The rate feels slow, which is part of why it is hard to take seriously in any single month. But spaceflight turns small rates into large consequences by giving them time. A spacecraft can keep moving, the crew can keep working, and the clock can keep running. Meanwhile, the skeleton quietly negotiates with an environment that no longer asks much of it. What makes unloading harder to manage than a discrete injury is its relationship with normal function. A crew member in orbit can perform every task the mission requires, operate systems, conduct experiments, move through the station, sleep well, while the bone loss continues. There is no performance indicator that trips. There is no moment when the adaptation announces itself as a problem. The mission looks healthy right up to the point where it ends, and the body meets a world that expects what it no longer fully has. One reason the problem persists is that the body is good at adapting. In missing load, it may reduce investment in regions where the environment seems to demand less. That is sensible for the environment the body is actually living in. It becomes a liability for the mission that follows. The body may begin adjusting to an absence of demand. The mission still expects strength to be there. This is why the bone question belongs inside spacecraft design discussions, not only in a medical log. Power, shelter, and navigation can all be solved well. But the crew arrives with a body shaped by Earth, and if that body keeps receiving the wrong mechanical signal, physiology becomes part of the architecture. It cannot be added as a footnote after the vehicle is drawn. The problem requires decisions before launch, precisely because the adaptation happens continuously throughout the mission, with no pause and no visible warning. There is no point during transit where a mission team can decide retroactively that bone protection was insufficient and add resources to fix it. The mass budget, the exercise hardware, the pharmacological supply, the monitoring capability, all of it has to be on board when the vehicle leaves. What is not carried cannot be added. The loading signal that Earth provided automatically and without cost has to be replaced by deliberate design before the door closes, and the adequacy of that replacement has to be validated before the mission departs, not discovered in orbit. The numbers help. A percentage on a scan becomes concrete when it belongs to a hip that has to hold weight in a pressure suit, or a spine that has to steady a person reaching for a tool on ground no one has walked before. Measurement does not exaggerate. It keeps the language honest when the mission timeline extends past anything that has been tested. So the handrail holds more than a floating body. It holds a living structure being asked, quietly and persistently, how much strength the new world seems to require. The answer the body gives will matter most when the mission finally needs that strength to still be there. That question is not new. Long-duration spaceflight has been raising it since the first station missions documented measurable density changes in returning crew members. What has changed is the destination. Station missions return crews to Earth, where recovery can begin immediately under full gravity and with full medical support available. Deep space missions do not have that recovery option at the end of the transit. The skeleton that arrives at Mars has to be functional on arrival, not 6 months after it. The research community that studies this problem is distributed across space agencies, universities, and medical institutions on several continents. NASA's Human Research Program maintains bone loss as one of its 5 identified top risks for deep space exploration, alongside radiation, behavioral health, sensory-motor adaptation, and nutrition. The classification is not bureaucratic. It reflects a research-informed judgment about which physiological hazards require the most intensive study and mitigation before long-duration missions beyond low Earth orbit can be conducted with acceptable risk. The 5-risk framework also captures why bone loss cannot be addressed in isolation. The interactions between radiation and bone metabolism, between nutrition and remodeling, between exercise and cardiovascular function, and between sleep, circadian rhythm, and systemic physiology mean that countermeasure design for one system has to account for its effects on the others. Bisphosphonates that protect bone may interact with radiation-induced DNA repair in bone progenitor cells in ways that are not yet characterized. Exercise protocols that protect both bone and cardiovascular fitness have to be designed with the constraint that exercise time is finite and has to serve multiple systems simultaneously. Integrated countermeasure strategies, designing the whole physiology management protocol as a system rather than a collection of individual interventions, are where the field is moving and where the most relevant progress is being made. The practical urgency of this research is tied to mission schedules. Each year of additional study before the first Mars mission launch reduces the uncertainty that crew members will carry into the longest and most physiologically demanding human journey ever attempted. The work happening now in laboratories, bed rest facilities, and on the ISS is preparation for missions that have not yet been approved. The people doing it are building knowledge that future crews will depend on. Under a microscope, a thin slice of living bone looks like a quiet lattice. Nothing is failing. No alert is visible, but two populations of cells are already running opposite operations on the same material. Osteoclasts dissolving old bone and releasing its minerals. Osteoblasts laying fresh matrix in their wake. This remodeling loop never stops. It is how bone responds to the mechanical world around it. Load arrives, the cells read it, and the balance shifts toward building. Load disappears, and the balance shifts the other way. That shift is the mechanism. In microgravity, where the continuous pressure through the hips and spine has gone quiet, the loop does not stop. It keeps cycling, but with the signal that drives formation reduced. The osteoclasts keep removing material at roughly their normal pace. The osteoblasts, lacking the mechanical cue that tells them how much structure the environment seems to require, fill back less than was taken. The deficit accumulates one remodeling cycle at a time. The remodeling cycle operates on a timescale of weeks to months. Osteoclasts typically resorb a remodeling unit of bone over about 2 to 3 weeks. Osteoblasts then fill the resorption cavity with new matrix over the following 2 to 3 months. The cycle is sequential, not simultaneous, which means that bone is always in some state of partial remodeling across its surface area. In a healthy individual under normal loading, the amount filled in closely matches the amount removed. In microgravity, where the signal that drives formation is reduced, the fill-in is incomplete and the net result is less bone volume per cycle. The danger is not visible at the cell level. No single remodeling cycle produces a detectable change. What makes it consequential is time. Each cycle that fills back slightly less than was removed leaves the skeleton fractionally lighter than it was before. Over a 6-month crossing, hundreds of those cycles run. The accumulation is where the problem lives, not in any single cellular event that could announce itself. One reason the problem is hard to see is that success can hide it. Crew performance can look strong, vehicle routines can stay orderly, mission clocks keep moving. Only later does the question tighten, around what the body carried through the transit and what it quietly set aside when the world stopped asking. Another reason is that bone does not answer with one simple switch. Density can shift in one direction, structure in another, and practical strength in a third. A scan may show part of the picture while a suited step or an awkward landing reveals something different. The concern is cumulative capability, not instant ruin. There is dignity in the countermeasures too. Daily loading in orbit is a quiet discipline. Every strapped run and every resisted pull is a negotiation with an environment that does not naturally ask enough from bone. The crew already knows that weightlessness is not pure freedom. The skeleton keeps a different account, and the exercise session is the daily deposit. So the quiet image changes. A thin slice under a microscope no longer shows only calm movement. It shows a living structure negotiating with absence. The force that shaped bone on Earth has gone faint, and the body is deciding what strength the new world seems to require. That decision, made at the cellular level, one remodeling cycle at a time, may become one of the real boundaries between reaching deep space and living there well. The timing of the cycle matters for understanding why the deficit compounds. In a normally loaded skeleton, resorption and formation run on overlapping schedules across thousands of remodeling sites simultaneously. The total bone surface at any given time contains sites being excavated, sites being refilled, and sites already complete. When loading drops, new resorption sites keep opening at roughly the normal rate, but the signal that closes them, that drives osteoblasts to fill the cavity fully and promptly, is weakened. Partly filled cavities persist longer. More sites accumulate in an incomplete state. The result is not a mass disappearance of bone, but a quiet reduction in the fraction of each cycle that gets replaced. This is also why the problem is not immediately reversible. When a crew member returns to Earth and loading resumes, the osteoblast response rebuilds. but the sites already in various states of partial fill have to complete their current cycle before the next round can begin. Recovery takes the same weeks to months that the cycle always takes. The body cannot rush the biology. It can only restore the signal and wait for the machinery to catch up. Sclerostin is a protein produced by osteocytes that inhibits bone formation by blocking the Wnt signaling pathway. In microgravity, sclerostin levels increase, which suppresses osteoblast activity and contributes to the formation-resorption imbalance. This makes sclerostin a pharmacological target. Drugs that inhibit sclerostin, such as romosozumab, have been shown to increase bone formation in clinical settings for osteoporosis treatment. Research is investigating whether anti-sclerostin therapy could be adapted as a spaceflight countermeasure, providing a biological lever to push the remodeling balance toward formation even in a reduced load environment. The Wnt pathway that sclerostin regulates is one of the primary cascades translating mechanical load into bone cell activity. It is also sensitive to fluid flow within bone. When bone is strained, fluid moves through the canalicular network and osteocytes detect it. In microgravity, that fluid flow stops. No strain, no movement, weakened Wnt signal, the chain from a floating astronaut to a changed cellular chemistry in the trabecular lattice of the hip is that direct. And because the link is precise, it is a therapeutic target. Cortical and trabecular bone respond differently to microgravity unloading, and that difference matters for fracture risk. Trabecular bone, the spongy internal lattice in vertebral bodies and the ends of long bones, has higher metabolic activity and remodels faster, showing larger percentage losses during spaceflight. Cortical bone, the dense outer shell, is more metabolically stable and changes more slowly. The femoral neck contains a combination of both. Its trabecular core can thin significantly while the cortical shell appears structurally similar on standard imaging, which means measurements focused on cortical geometry can underestimate the functional impact of interior structural loss. Bone quality, as distinct from bone quantity, is what makes that distinction clinically meaningful. Two bones with identical mineral density can have very different fracture resistance depending on the architecture of their trabecular network. Spaceflight tends to reduce both density and trabecular connectivity, compounding the fracture risk beyond what a density number alone captures. High-resolution peripheral quantitative computed tomography, which images trabecular architecture in detail, is being applied to astronaut populations to assess these quality changes, a more informative approach to fracture risk prediction than density measurement alone. A crew member can float through an entire station day, eating, working, sleeping, without the femoral neck registering any of it as load. The hatch does not feel heavy, the corridor has no floor. Nothing asks the skeleton to carry anything. Zero gravity is a description of that condition. Unloading is what it does to bone. Every hour without foot contact is an hour when the remodeling balance receives a reduced signal and the osteoclast-osteoblast cycle runs in a direction that serves a lighter world. The key distinction is between a dramatic event and a quiet environmental condition. A dramatic injury announces itself. Unloading does not. There is no warning, no threshold moment, no signal from the body that the balance has shifted. The process is not an emergency. It is an adjustment. The skeleton is doing exactly what bone should do, responding to what the world is asking. The problem is that the world the body is reading and the world the mission will eventually need are two different places. Mechanosensation is the process in question. Osteocytes, cells embedded in the bone matrix, sense mechanical strain and communicate it through a network of thin channels called canaliculi. When strain is present, this network carries signals that promote bone formation. When strain drops below a threshold, the signal weakens. In microgravity, a crew member's weight-bearing bones receive far less strain than they would standing, walking, or even sitting under Earth gravity. The osteocyte network reflects that, and the remodeling balance responds. The femoral neck, the lumbar vertebrae, and the pelvis are where density loss has been measured most consistently in returning crew members. Those are also the structures most relevant to surface operations. The hip that must absorb a step in a pressure suit, the spine that must stabilize a person lifting equipment on uneven ground. One misunderstanding that complicates public discussion is that sleep or rest is the mechanism. A crew member sleeping poorly in a strange environment is not the issue. Sleep position does not change the mechanical signal the skeleton receives in microgravity. A person can sleep 8 hours normally and still wake into a cabin where the hip and spine are being asked for nothing. The loading environment is the same awake or asleep. What the skeleton adapts to is not rest, it is continuous unloading. Each monthly increment sounds manageable in isolation. It is only across the full duration of a transit, 6 months, 9 months, longer, that the arithmetic becomes a design problem. A spacecraft can be traveling flawlessly while its crew arrives at the destination carrying a density deficit that no scan during transit turned into an obvious operational concern. The mission can look normal while the adaptation continues. Countermeasures are the mission's attempt to write a different message into that environment. Exercise devices create strain. Nutrition supports the cellular processes. Monitoring tracks whether the strategy is working. But none of these tools restores the continuous passive load that comes from standing on a planet. They are active interventions into a problem that Earth solved passively. That distinction, active effort versus passive environment, is what makes the countermeasure question a permanent one, not a solved one. The honest boundary here is that the problem is real, measurable, and not yet solved for long durations. Short missions have been managed. The protocols exist and have been tested. What has not been tested is whether those protocols scale to a multi-year mission or protect a crew arriving at Mars for the first time after the longest continuous unloading period in mission history. That boundary is the reason the field continues to study the underlying mechanism rather than treating the countermeasures already in use as a complete, sufficient, and settled final answer to the problem. The message that bone is receiving in microgravity is not silence. It is a reduced signal, and a reduced signal is still a signal. The osteocyte network is still active. It is still communicating between cells, still influencing the balance between resorption and formation. What it is communicating is a recalibrated picture of the environment. A world that asks less, a world where less structural investment is required to meet the demands being placed on the skeleton. From the biology's perspective, this is correct information. The skeleton is adapting efficiently. The problem is entirely one of mission design. The body is right about the world it is currently living in, and wrong about the world it will eventually need to work in. This is why the false message framing is precise. The message is not malformed. It is accurate to its conditions. Zero gravity in orbit genuinely does ask less of the femoral neck than Earth does. The skeleton is not malfunctioning when it reduces investment in a region that is no longer being loaded. It is functioning exactly as designed. What the mission requires is a body that has been, in some sense, deceived, kept strong for demands that the current environment is not making, so that it is ready for demands that a future environment will make without warning. Exercise countermeasures are the mechanism of that deception. Loaded squats and resistance pulls convince the osteocyte network that the world still requires strong hips and a strong spine. The network responds to strain regardless of where that strain comes from: gravitational load, muscle contraction, or a machine producing resistive force. As long as the mechanical message arrives in the right place at the right magnitude and frequency, the remodeling balance can be kept closer to the formation side. The countermeasure is not solving the problem of microgravity. It is providing a false signal that overrides the true signal long enough for the mission to succeed. Whether that override is sustainable for a multi-year mission at the quality achievable on current hardware is the operational question. The biology of the false message is well enough understood to design interventions around it. What remains uncertain is whether those interventions can maintain a strong enough false signal continuously across the full duration of a Mars mission in hardware that is limited by mass and power budgets, operated by a crew that has many other demands on their daily schedule. Unloading also affects bone in ways that go beyond density. The geometry of the skeleton under load keeps bones aligned along stress lines that make them efficient at carrying force. Without that directional stimulus over months, subtle geometry changes can occur in how trabecular struts are oriented inside the femoral neck. A bone that has lost not just mass, but the alignment that made that mass effective against predictable forces is different from a healthy bone of the same measured density. The social framing of the problem has historically made it harder to take seriously. Bone loss in space sounds like a medical curiosity, a slow-moving background concern next to the dramatic risks of launch, vacuum, radiation, and re-entry. But chronic risks have a specific danger that acute risks do not. They are easiest to ignore precisely while they are accumulating. A bone that fractures at the bottom of a ladder on Mars is not less serious than a bone fractured in a dramatic event. The difference is only when the damage accumulates, not what it costs the mission. And unlike a sudden event that forces an immediate response, the slow accumulation can reach its threshold quietly, at exactly the moment when mission operations are placing maximum demand on the affected structure. The mechanobiology of bone goes deeper than the simple on-off of load and no-load. The skeleton does not respond to the total load applied in a day as a simple average. It responds to peak loads, to loading frequency, and to whether the loading pattern is varied or monotonous. Research on bone adaptation suggests that repetitive identical loading gradually loses its stimulus value. The skeleton adapts to a specific pattern and eventually stops responding to it as strongly. Varying the loading pattern, introducing unexpected directions, and applying brief high-intensity loads are more effective stimuli than sustained low-level loads. This finding has implications for countermeasure design. 2 hours on a treadmill with a harness producing a consistent vertical force is a different stimulus from a varied ground surface that creates different loading vectors with every step. Spaceflight provides an unusual opportunity to study bone biology in ways that are difficult on Earth. Comparing a twin who flew a long mission with a twin who stayed on Earth eliminates genetic confounders and isolates the spaceflight effect. Long-duration mission data of this kind confirmed the expected density changes and highlighted the body's capacity for substantial recovery after return. A reason for measured optimism, and also the reason the question of whether that recovery persists across longer missions remains one of the more important open ones in the field. One to 1.5%. That is the density loss per month in vulnerable weight-bearing regions that NASA risk documentation puts to the process. The number comes from dual-energy X-ray absorptiometry scans taken before and after missions. DEXA measures the hip and lumbar spine. Not how a person feels, not how capable they look during a routine station day, but what the remodeling balance has quietly decided to remove. A scan is powerful because it turns a quiet biological process into something mission planners can argue over. The percentage is not the whole body. It does not capture how prepared or skilled a crew member feels. It does show whether hidden reserve is moving in the wrong direction before a surface task exposes it. The specific bones targeted by DEXA scanning in astronaut health monitoring are the ones that answer the question of mission readiness: total hip, femoral neck, and lumbar spine. These are weight-bearing regions. They are also what a crew member needs to land, exit a vehicle, carry equipment on an uneven surface, or recover from a fall. The scan is not tracking general wellness, it is tracking the structures most relevant to what happens when orbit ends. The numbers from ISS missions cluster around 1 to 2% loss per month in the lumbar spine and total hip, with individual variation that is difficult to predict in advance. Some crew members respond to countermeasures well. Others lose more despite following the same protocols. The variation is not reassuring. It means the average hides a range, and the range includes outcomes that are medically significant. What the scan cannot show is trabecular microarchitecture, the fine internal structure of cancellous bone that determines how load is distributed across a cross-section. Density is one measurement, structural quality is another. A hip can have an acceptable density score, while its internal lattice has thinned in ways that reduce its capacity to absorb impact. Density and architecture can diverge, and the tools that capture both are not always available before a crew member takes a first step on a new surface. Fracture risk is the clinical concern that density loss is pointing toward. Below a density threshold, the probability of fracture under stress increases. A landing, a stumble in a pressure suit, lifting heavy equipment in low gravity. None of these are unusual mission activities, and all of them generate forces on the femoral neck and lumbar vertebrae. The question the scan is trying to answer before it is too late is whether those structures can still do the work the mission will require. The scan also reveals something about countermeasure effectiveness. Before and after comparison across a mission tells researchers which exercise protocols, which nutritional approaches, and which pharmacological interventions preserve density most effectively. That feedback loop is how current protocols were developed, and it is how better ones will be designed. The scan is not just a risk flag, it is a research instrument generating the evidence that future missions will depend on. The honest message from the scan record is that current countermeasures manage the problem on station-length missions, but do not eliminate it. Crew members return with measurable losses. Recovery happens over months after landing, often but not always reaching baseline. The scan at return is a verdict on how well the mission's physiology strategy worked. For longer missions, that verdict has not yet been written. A 6-month ISS mission can result in 5 to 10% total hip bone mineral density loss if countermeasures are inadequate. With current protocols, losses are typically lower, often 1 to 3% total, but still present. A crew member starting a Mars transit with normal bone density and losing 1.5% per month could arrive at Mars with 15 to 20% less hip density than they left with, depending on transit duration and countermeasure effectiveness. The fracture risk implications of that range are clinically significant. Scan data has also revealed regional differences in how spaceflight affects bone. Weight-bearing regions lose density. The arms typically do not, they may even gain slightly, because astronauts use them constantly to move through the station. That selectivity confirms the mechanism. Regions that stop being loaded lose density. Regions that stay loaded hold their own. Mission planners can read this pattern directly. The structures that need protection are the ones that Earth gravity loaded every day, and the countermeasure has to put directional load back into those specific places. Longitudinal tracking of crew members across multiple missions has added a further dimension. Some individuals who have flown multiple times show cumulative bone losses that do not fully recover between flights. Whether repeated spaceflight produces incremental permanent deficit is a question that the scan record is beginning to answer. For crew members selected for long duration or repeated deep space missions, the lifetime exposure question may matter as much as any single mission's outcome. The comparison point that makes the DEXA numbers clinically concrete is the T-score used in osteoporosis diagnosis. A T-score compares an individual's bone density to a young adult reference population. A T-score below -2.5 defines osteoporosis. A score between -1 and -2.5 defines osteopenia. Crew members who begin a mission with normal T-scores in the high positive range can end a station-length mission with scores that have moved measurably toward the clinical concern thresholds, not necessarily crossing them on the first mission, but with repeated or longer missions. The arithmetic of accumulated deficit becomes clinically relevant. The scan as a pre-mission tool matters as well as a post-mission one. Baseline bone density varies significantly among healthy adults, and a crew member who begins a mission with relatively lower baseline density has less reserve before reaching clinical concern thresholds. Pre-mission DEXA scanning is standard in astronaut health monitoring and is used to set individualized targets for countermeasure effectiveness. A crew member whose baseline places them at the lower end of normal may require more aggressive in-flight countermeasure protocols than one who begins with higher reserve. The scan is not only a verdict on what happened, it is a starting point for planning what needs to happen next. The measurement frequency matters as much as the measurement tool. A single pre-mission DEXA and a single post-mission DEXA document the change, but cannot tell researchers when in the mission the change was fastest, whether it plateaued, or whether a countermeasure adjustment mid-mission altered the rate. In-mission scanning, where equipment and crew time permit, provides a longitudinal curve rather than just two endpoints. That curve is considerably more useful for refining protocols. Some ISS missions have included mid-mission measurements, and the data from those scans have been valuable for understanding how loss rates vary over time within a single mission. Future vehicles supporting longer missions need to carry the scanning capability to generate that longitudinal record, rather than arriving at destination knowing only that the loss occurred, not when and how fast. The in-mission scan also provides an early warning function. A crew member losing density faster than expected early in the mission may benefit from adjusted exercise intensity, pharmacological support, or nutritional modification before the deficit compounds. Without mid-mission data, that intervention opportunity is missed. The scan becomes reactive rather than proactive, a record of what happened rather than a tool for preventing what could still be changed. What the full scan record from the ISS era has established is a reference dataset that did not exist 30 years ago. Pre-mission baselines, mission end values, recovery curves, and longitudinal multi-mission data together paint a picture of how the human skeleton responds to spaceflight over months and years. That picture is detailed enough to support the current countermeasure protocols and to identify where they fall short. For missions beyond Earth orbit, the record will be extended by the missions themselves, each adding data points to the curve that describes what human bone does in the environments that the mission timeline passes through. The Advanced Resistive Exercise Device on the International Space Station can generate up to 272 kilograms of resistive load. That specification matters because it was chosen with bone in mind. A standard treadmill floating freely would do almost nothing. The runner pushes off and drifts. The bungee harness system solves that by pulling the body toward the belt, creating a downward force the skeleton has to work against. It is a manufacturing problem. How do you reconstruct the signal Earth provides for free? That is why the machine matters even when it looks ordinary. A strapped run is not fitness theatre. It is a daily argument with the environment. Each resisted movement carries a mechanical argument that the skeleton still needs to maintain the structures where future work will need them. The ARED and CVIS systems on ISS represent the most refined version of this argument currently deployed. ARED can produce squat, deadlift, and heel raise loads that approach what a person would generate training in a gym on Earth. CVIS provides cardiovascular stimulus. Together they address muscle atrophy and cardiovascular conditioning alongside bone, because these systems degrade together and their interactions matter for mission readiness. The gap these devices cannot close is time. Crew members use them for roughly 2 hours per day. The remaining 22 hours are still spent inside microgravity. The osteocyte network that governs bone remodeling is reading the whole day, not just the exercise window. 2 hours of high-load stimulation does not undo the signal from the other 22. It competes with it, and the evidence suggests that competition is only partially won. Individual response variability makes the problem harder to manage at the program level. Some crew members maintain density through a 6-month mission with minimal loss. Others follow the same protocol and lose significantly more. The underlying biology that produces this variability is not yet well enough understood to predict in advance who will respond well and who will not. That makes pre-mission screening limited and post-mission scan results the main tool for knowing whether the strategy worked. Equipment reliability is a second constraint. Machines in microgravity develop wear patterns that differ from ground-based equipment. ARE has experienced mechanical failures on ISS. When the device is unavailable for days or weeks, crew members improvise or reduce exercise intensity. During those gaps, the bone receives less stimulus, and the mission's countermeasure record develops holes. The exercise system is not a backup system for a redundant function. It is the primary defense against a process that does not pause while the hardware is being repaired. Future exercise systems for deep space missions face a mass and volume problem. A heavier, more capable device is better for bone. It also adds to a spacecraft budget that is constrained at every level. Mission designers have to decide how much payload capacity to allocate to exercise hardware against competing priorities. That trade-off is not technical. It is a choice about how seriously the physiology problem is weighted against other mission requirements. The exercise harness is a daily reminder that the solution the mission carries is not equivalent to the solution Earth provides for free. What the planet does effortlessly, passively, and continuously across the full waking and sleeping day requires machinery, scheduled time, physical effort, and repair cycles to approximate. The approximation is not enough to eliminate bone loss. It is enough to make the mission manageable. Whether that management level is enough for missions longer than those currently flown is still an open question. Whole-body vibration research, short-arm centrifuge trials, high-intensity interval exercise protocols, and targeted pharmacology represent the active fronts of countermeasure development. None has yet displaced the core arid and treadmill approach as the primary bone protection strategy on ISS, but each has contributed to understanding what drives the mechanobiological response well enough to design better interventions. The exercise hardware planned for future gateway and transit vehicle configurations has been designed with lessons from this research. The type of load matters, not just the amount. High-impact loading, the kind generated by jumping or running on a hard surface, is particularly effective at stimulating osteoblast activity through the mechanosensory pathway. In microgravity, true high-impact loading is impossible without a harness system that can absorb the reaction. Even with ARED and treadmill systems, the impulse loading pattern that walking on Earth generates thousands of times per day is difficult to reproduce in a microgravity cabin. The bones respond to impact differently than to slow, sustained loads, and that difference matters for which specific structures are most effectively protected. Vibration therapy has been explored as a supplementary approach. Whole-body vibration at specific frequencies can stimulate bone formation in bed rest studies. The mechanism is not fully understood, but the osteocyte mechasensory network appears to respond to low-level vibration as a load signal. ISS experiments have tested vibration devices as additions to the exercise protocol. Results are mixed, and vibration alone does not substitute for resistive loading. But the concept illustrates that the field is actively looking for ways to extend the countermeasure toolkit beyond conventional exercise. Pharmacological approaches and exercise interact in ways that can work together or against each other. Bisphosphonates reduce osteoclast activity, which can reduce bone loss. But the remodeling cycle also repairs microdamage in bone, and suppressing that cycle too aggressively can allow microcracks to accumulate. Combining bisphosphonates with intense resistive exercise, which generates significant bone stress, requires careful monitoring of the remodeling balance. The countermeasure stack is not simply additive. Managing it requires understanding how each component affects the others. The role of astronaut scheduling in countermeasure effectiveness is underappreciated. ISS crew members have full schedules including maintenance activities, science operations, communications, and daily life tasks. Exercise is scheduled within that framework, and schedule pressure can lead to shortened or skipped sessions. Studies of crew exercise compliance on ISS have shown that actual exercise duration often falls below the prescribed 2-hour daily target. Real-world compliance, rather than protocol design, may be a significant factor in the variation in bone outcomes between crew members. This observation has led to redesigning exercise protocols to be more time-efficient, higher intensity for shorter durations, as well as to scheduling exercise as a protected block rather than a flexible one. Nutrition during spaceflight faces constraints that ground-based nutrition does not. Food on ISS and future vehicles has finite shelf life, limited variety, and requires preparation in microgravity. Some nutrients degrade over storage time, meaning that foods launched at the beginning of a long mission may have reduced nutritional value by the time they are consumed. Calcium and vitamin D content of space food has been carefully validated, but the bioavailability of calcium from space food sources in the absence of normal gravitational loading and gut motility may differ from ground-based consumption. The interaction between diet, gut physiology, and bone metabolism in microgravity is an active area of research with implications for menu design on long missions. The total calcium cycle during a spaceflight is negative across most missions without countermeasures. More calcium leaves the body through urine and feces than is absorbed from food and supplements. This net calcium loss drives the bone resorption that produces measurable density changes. Interventions that reduce urinary calcium excretion, including hydration management, dietary acid-base balance, and specific medications, can help maintain a less negative calcium balance. But bringing the calcium balance positive, which is required for net bone formation rather than just reduced resorption, is harder to achieve in a low-load environment, regardless of calcium intake. The skeleton needs both the mineral supply and the mechanical signal to respond to that supply by building new structure. "2 hours of exercise per day. That is the current countermeasure prescription on ISS for bone and muscle protection combined. 2 hours leaves 22. For those remaining hours, the skeleton still lives inside microgravity, still receives no gravitational load through the hips and spine, and still runs a remodeling balance shaped by that absence. The exercise matters. The gap it does not fill also matters. Calling the fightback a cure would make the problem too neat. The better word is management. Management can be disciplined and effective. It can also leave a margin that depends on duration, equipment health, individual response, and the condition of the body at the end of transit. Exercise is not the only tool available. Nutritional intervention includes calcium and vitamin D supplementation, because bone remodeling requires adequate mineral availability, and the vitamin D pathway governs calcium absorption. Crew members on ISS have had dietary intake carefully monitored, and deficiency has been linked to worse bone outcomes. Nutrition cannot replace mechanical load, but it can reduce the metabolic cost of running a remodeling balance already stressed by the environment. Bisphosphonates have been studied as a pharmacological countermeasure. These drugs inhibit osteoclast activity, slowing the resorption side of the balance. Combined with exercise, they have shown the ability to reduce density loss in spaceflight analog conditions. The concern is that they suppress one side of a cycle without addressing why the cycle is running in the wrong direction. Long-term consequences of that suppression across missions much longer than current trials remain incompletely characterized. The interaction between tools matters as much as any individual one. Exercise creates mechanical stimulus. Nutrition supports the cellular response. Bisphosphonates slow resorption. Monitoring checks whether the combined strategy is producing the intended outcome. None of these works in the way gravity works, continuously, passively, and across the whole body without effort. They compensate for an absence rather than fill it. The word countermeasure carries the honest admission inside it. A countermeasure is a response to a hazard the mission environment cannot eliminate. It acknowledges the hazard is present and managed, not absent or solved. That distinction is not rhetorical. It is why the equipment rack is an essential mission system and not a wellness amenity, and why its design, mass, reliability, and scheduled maintenance time belong in the same conversation as propulsion and life support. The gap between management and cure becomes most visible when mission duration extends. 6 months of managed bone loss under the current ISS protocol leaves crew members with measurable deficits that recover over months of Earth living. Whether the same protocols protect a crew across a 2 to 3 year Mars mission is not known. The countermeasure infrastructure built around station-length missions is the best available baseline. It was not designed for the problem it may eventually face. The word management also covers the monitoring side of the equation. Regular DEXA scanning during a mission allows the medical team to track whether an individual crew member is losing more density than the protocol should allow. If loss rates exceed expected ranges, the protocol can be adjusted. More exercise time, modified nutrition, consideration of pharmacological support. This adaptive management approach treats the countermeasure not as a fixed prescription, but as a continuous negotiation between the individual's biology and the mission environment. The limits of adaptive management become apparent on long transits where communication delays make real-time medical support impossible. A crew 9 months from Earth with a communications delay of 20 minutes each way is making medical decisions with delayed input. The bone monitoring data reaches Earth's medical teams with a delay, the response comes back with a delay, and the crew has to implement changes in a situation that has continued to evolve. For station missions, Earth-based medical teams can respond to scan data within hours. For a Mars transit, the effective medical response window is measured in days. That lag changes what management can realistically mean. Genetic factors contribute to why individuals respond differently to microgravity exposure. Studies of ISS crew members have identified genetic variants associated with faster or slower bone loss rates. RANKL and OPG pathway genetics, vitamin D receptor polymorphisms, and bone morphogenetic protein variants all influence baseline bone density and remodeling rate. This research is early, but suggests that pre-mission genetic screening may eventually allow mission planners to anticipate who needs more aggressive countermeasures. The goal is not to exclude crew members, but to personalize the protocol so that the mission's physiology management starts from an evidence base tailored to each individual. Emerging pharmacological agents offer a different mechanism than bisphosphonates. Sclerostin inhibitors, which target the WNT signaling pathway to promote bone formation rather than suppress resorption, have shown promising bone-building effects in osteoporosis trials on Earth. The logic for spaceflight is different from bisphosphonates. Instead of slowing the cell removing bone, these agents stimulate the cell building it. If the formation side of the remodeling imbalance can be amplified, the deficit between what osteoclasts remove and what osteoblasts replace might close more quickly. Clinical trials in spaceflight analog populations are underway, and preliminary results are informing whether the next generation of pharmacological countermeasures will be resorption-focused, formation-focused, or a combination of both. The practical constraint on any pharmacological countermeasure in spaceflight is the medication management system the mission carries. Drug stability under radiation exposure, temperature fluctuation, and long storage durations is not guaranteed to match Earth pharmaceutical standards. A medication that is effective in a clinical trial on Earth may degrade more quickly in the space radiation environment, altering its potency over a multi-year mission. This is not a barrier to pharmacological countermeasures, but it is a variable that does not appear in the Earth-based trial data that informs their use. Mission pharmacology research has to account for storage environment effects in ways that ground-based clinical research does not. The cumulative picture from a full mission is not just the sum of individual countermeasure effects. Exercise, nutrition, pharmacology, and monitoring interact. An adequate calcium intake supports the cellular response to exercise loading. A bisphosphonate that suppresses osteoclasts may change how bone responds to mechanical stimulus. Sleep quality, stress hormone levels, and circadian rhythms each influence the remodeling cycle that all other countermeasures are trying to correct. Managing bone health on a Mars transit is not a single system problem solved by a single drug or a single exercise session. It is a system-level challenge requiring coordinated management across every relevant physiological pathway for the entire mission duration. One practical limit of the current ISS-derived approach is that it was optimized for missions of roughly 6 months. The protocols, equipment specifications, and monitoring schedules were developed and refined through decades of missions within that duration range. Extending them to a multi-year Mars transit is an extrapolation, not a validated application. The assumption that protocols sufficient for 6 months will remain sufficient at 18 or 24 months has not been tested. It may be true. It may be that the early months of a mission produce the steepest bone loss, and that later months see a plateau, making the protocol scale reasonably. Or it may be that cumulative unloading creates progressive losses that accelerate rather than stabilize as the mission continues. The data to distinguish between these scenarios does not yet exist at the durations that matter. The fatigue and motivation factors that affect exercise compliance are also underappreciated components of countermeasure effectiveness. A crew member who is exercising 2 hours per day, every day, across a 9-month transit to Mars is maintaining a level of physical discipline that few people sustain indefinitely on Earth. Psychological research on long-duration isolation missions has documented declines in motivation, mood, and behavioral compliance in the middle phases of a mission, sometimes called the third quarter phenomenon. If exercise compliance drops during that phase, bone losses accelerate at exactly the point in the mission where the cumulative deficit is already largest. Designing countermeasure systems that are robust to motivation fluctuations through automation, variety, social accountability, or exercise modalities that crew members are willing to maintain even on difficult days is as important as the biomechanical engineering of the devices themselves. The honest cost of the fightback is visible in what a spacecraft has to carry to enable it. Mass, volume, power, maintenance capacity, scheduled crew time, pharmacological inventory, and monitoring infrastructure are all real mission resources allocated to a problem that a planet solves for nothing. That allocation is not a luxury. It is what separates a mission that arrives with capable crew members from one that does not. A Mars transit, under current propulsion estimates, runs between 6 and 9 months each way. At 1 to 1.5% density loss per month in the hip and lumbar spine, a crew arriving at Mars could carry a measurable deficit into the first surface operations. The hatch opens, and for the first time in months, gravity, 38% of Earth's, is present. That returning load meets a skeleton that has been adapting its remodeling balance throughout the entire crossing. It was not idle, it was adapting, and the problem is what it was adapting toward. This is why arrival is a harsher test than transit routines suggest. A crew can look fully operational during the crossing and still meet a demand at the hatch that the transit's countermeasures did not fully prepare for. Mars does not ask whether the vehicle arrived on schedule. It asks whether the people inside can still function as mission systems under 38% gravity after the longest continuous unloading period in human spaceflight history. The specific tasks that begin at arrival are not theoretical. Descent and landing produce vibration and g-forces the body has to withstand after months of unloading. Exiting the lander requires negotiating a hatch and steps in a pressure suit. First surface EVAs involve carrying equipment, working on inclined terrain, and using tools that require grip and postural stability. Any fall in that environment, on uneven, undocumented ground, far from medical care, involves a skeleton that has spent months adjusting its density to a world that asked nothing of it. Mars gravity at 38% of Earth's provides more load than orbit, but not enough load on its own to quickly restore density that was lost during transit. The remodeling balance that shifted toward resorption during the crossing does not immediately reverse when the feet touch ground. Recovery begins with the return of directional load, but the timeline for that recovery under Mars gravity is not the same as recovery under full Earth gravity. That difference has never been tested in humans. Surface tasks create an asymmetry in risk that the mission timeline cannot smooth away. A crew arriving at Mars with significant density loss in the femoral neck and lumbar spine is not starting from baseline, they are starting from deficit. The mission's physical demands begin immediately upon landing. The body's recovery from transit begins on the same day. These two processes run in parallel, and the margin between them is what fracture risk lives in. The countermeasure record from transit will be the mission's starting point for managing this. A crew that maintained density well during the crossing arrives with less deficit and more margin. A crew whose density loss was higher, whether from equipment failure, individual variability, or mission timeline compression, arrives with less. Mission designers cannot control individual biology, but they can control the quality and reliability of the countermeasure system that runs for the entire transit duration. The deeper lesson from the Mars arrival frame is that bone health is not a medical problem that sits alongside the mission. It is a mission-critical variable that shapes what the first hours, days, and weeks on the surface can and cannot include. A hip fracture on Mars is not a medical emergency with a hospital 40 minutes away. It is an event that changes whether the mission succeeds. The Mars surface schedule for the first crewed missions has not been finalized, but planned activities include immediate deployment of life support systems, initial habitat setup, EVA suit checkout, and early science surveys. These are not passive activities. They require physical capability from a body that has just completed the longest continuous unloading period in human history. Mission planners cannot assume that landing ends the physical challenge. In many respects, it is where the physical challenge begins. Emergency scenarios compound the risk. A crew member who falls outside the lander during the first EVA is not in a controlled rehabilitation environment. They are in a pressure suit, at distance from the vehicle, with reduced muscle strength, disrupted balance, and bones that spent months adjusting their density downward. Suit mass adds load. Martian terrain is undocumented. Medical support is limited to what the crew can provide for each other. That combination is the operational argument for taking bone density seriously from launch day forward, not only once the surface is reached. Transit bone protection also matters for the return journey. A crew that spends 18 months on the Mars surface and then faces another 6 to 9 month return transit carries the combined physiological effects of transit, surface exposure, and transit again. The surface stay under 38% gravity may provide some bone loading benefit, but it also involves physical work, environmental stresses, and limited medical resources. Whether the surface stay helps or further stresses the skeleton depends on how well the surface countermeasure infrastructure works. Return transit bone protection begins with what the surface stay preserved. The arithmetic of a Mars mission makes the bone problem a design priority rather than a medical consideration. If a crew member loses 1% per month of hip bone density during a 9-month transit, arrives with 9% less density, works for 18 months on the surface at uncertain recovery, and then faces another 9-month return transit, the cumulative skeletal stress over the full mission is unlike anything that has been documented in a human subject. The missions that will test this will be making decisions at the edge of what the existing evidence base covers. What a fracture means on Mars is one of the starker aspects of the risk analysis. On ISS, a medical emergency that cannot be managed on orbit results in an emergency return to Earth within hours. That evacuation option does not exist on a Mars transit or surface mission. Everything the crew carries and every technique they have trained for becomes the full scope of available treatment. A femoral neck fracture, which terrestrial medicine manages with surgical fixation, would require improvised immobilization and extended reduced capacity crew operation, and the mission would continue regardless. Mission planners cannot set the acceptable bone loss threshold based only on what they would prefer to happen. They have to set it based on what is medically and operationally acceptable given the care available at destination. That standard is different for a surface mission with no evacuation option than it is for an ISS mission with emergency return capability. The bone density threshold for acceptable mission readiness on Mars is lower than the threshold for concern in a clinic in Houston because the context that determines what a fractured hip means is entirely different. Pre-landing preparation matters as much as transit countermeasures. Some mission concepts include a deliberate physical conditioning phase in the final weeks before Mars orbital insertion, an intensification of exercise protocols designed to drive as much bone formation stimulus as possible before the crew commits to descent. Whether this late transit push meaningfully shifts the density trajectory is uncertain, but the logic is straightforward. Whatever loading can be delivered before the hatch opens reduces the deficit the surface will expose. The body's response to intensified late transit exercise is one of the specific questions that future long-duration analog missions and bed rest studies are designed to address. The moment of first contact with the Martian surface also carries a physiological asymmetry that no simulation has fully replicated. The crew will have trained for surface operations, worn their suits in simulated environments, and practiced the physical tasks they expect to face. What they will not have experienced is those tasks performed in 38% gravity after months of near zero load. Simulation closes some of that gap. It does not close the gap between a simulated first step and a real one, taken by a skeleton that has been quietly adjusting its investment downward for the entire duration of the crossing. A boot print in weak gravity feels like an answer. Picture lunar dust pressed down by a real foot, holding the shape of a human step. Nothing about the image looks weightless. No one is floating past a wall. No alarm is sounding. The body has met a surface again. That is the uncomfortable part of partial gravity. It may feel like the answer while still being only part of one. The surface can look reassuring before anyone knows whether the skeleton is receiving enough repeated force to preserve long-term capability. That is the comfort. It is also the trap. Bone does not only ask whether gravity exists, it asks whether the load is enough, often enough, in the right places for long enough. A little gravity may help. It may help a lot. But the hard question is not whether the Moon or Mars gives the skeleton something to work with. The hard question is whether that something is enough for a body that has to live, work, fall, recover, and keep doing the mission. The Moon offers about 16% of Earth's gravitational acceleration. Mars offers about 38%. Both values are above the zero of orbital microgravity. What the biology needs to know is where the threshold lies. At what level does gravitational load preserve bone density, and at what level does it allow steady erosion? Neither lunar nor Martian gravity has been tested long enough, in a controlled enough setting, with enough human subjects to answer that question. Bed rest analog studies on Earth have given partial answers. Extended immobilization at 1G produces bone loss that resembles spaceflight bone loss, with some regional differences. Loss rates and patterns under simulated Martian gravity have been studied in rodent experiments and brief human centrifuge work, but not in subjects living under actual 38% conditions for months. Apollo crews spent days on the lunar surface. Future lunar and Mars crews may stay months or years, and the physiological record does not extend to that duration or that gravitational environment. What this means for mission planning is that partial gravity cannot be treated as a solved condition. A crew on the lunar gateway or a Mars surface habitat cannot be assured that surface gravity alone will maintain bone health without additional countermeasures. The exercise prescription, the nutritional strategy, and the monitoring protocol that apply during transit may need to continue on the surface. The surface is not the end of the bone problem. It may be a new version of it. The operational consequence is visible in surface habitat design. If a crew needs 2 hours of loaded exercise per day, even on the Martian surface, the habitat requires exercise infrastructure. That infrastructure requires power, floor space, maintenance capacity, and crew time. The layout of the habitat, the daily schedule, and the mass budget all reflect a decision about how seriously the physiology risk is taken. A boot print in the dust can look like arrival. The question of whether the body that made it is capable of everything the mission requires next is still a measurement problem, not a solved one. The lunar case is instructive because it is closer on the mission timeline. Artemis missions are returning crews to the lunar surface with stays measured in days to weeks initially, and the architecture envisions longer gateway-supported stays. The gateway habitat is in a near rectilinear halo orbit, which means crew members would be exposed to microgravity in the gateway and then transit to the surface for EVA activities. The bone loading question applies at every stage: microgravity in transit, microgravity in the gateway, 1/6 gravity on the lunar surface. Each environment provides a different loading level, and the cumulative effect of cycling through them over weeks or months has not been characterized at a scale sufficient for protocol design. Lunar gravity at 1/6 Earth gravity is even further below the threshold of uncertainty than Martian gravity. If the minimum effective load for bone maintenance is somewhere above 1/6 Ga, a real possibility, then lunar surface time may provide some loading benefit, but not enough to offset microgravity exposure in transit and in the gateway. Crew members might be losing density faster on combined lunar missions than on a straightforward ISS stay, simply because the mission architecture places them in multiple environments, none of which provides adequate bone loading, rather than one continuous microgravity environment where the countermeasure schedule can be maintained consistently. Short-duration Apollo stays are sometimes invoked to suggest that lunar operations are physiologically safe. Those missions lasted days and returned crews to Earth quickly, and post-mission recovery was correspondingly good. Future lunar missions that involve months on the surface and months in gateway orbit are closer in total exposure duration to an ISS mission than to Apollo. Invoking Apollo data to reassure against extended lunar presence is a category error. The comparison does not hold. What makes partial gravity ambiguous for bone is the osteocyte signaling threshold. Remodeling is not governed by a binary gravity switch. It operates as a graded response. More strain produces stronger formation signal, less strain produces weaker signal. Below some minimum strain threshold, the signal is insufficient to drive net bone formation. Whether lunar gravity produces strain above or below that threshold in the hip and spine of a specific crew member exercising in a specific environment for a specific duration is the calculation that current bone biology cannot perform with confidence. What can be said is that the strain pattern under partial gravity differs from both microgravity and full Earth gravity in ways that are not simply proportional. In microgravity, the compressive loading of body weight through the axial skeleton is absent. In partial gravity, it is present but reduced. The muscles that stabilize and move the skeleton under partial gravity have to generate different forces than they do under full gravity, because the equations of balance and movement change. These altered muscle forces produce altered bone loading patterns that do not simply scale linearly with the gravitational field. A person walking under 1/6 gravity moves differently than a person walking under full gravity, and the bone loading patterns their movements generate are different in ways that make simple percentage scaling unreliable. Picture a cylindrical module rotating slowly around its long axis. A crew member stands on the curved inner wall. Feet are in contact with a surface. The hips feel pressure. The spine has something to stabilize against. The skeleton is reading load. That load comes from spin, not from a planet. But bone does not require a planet. It requires force. A rotating habitat can provide that force by swapping centripetal acceleration for gravitational acceleration, spinning fast enough at a large enough radius that the floor pushes back. The principle is not new. What remains difficult is everything required to build it, operate it, and keep a human crew functional inside it. That is why the artificial gravity idea keeps returning in serious aerospace engineering. It is not nostalgia for science fiction imagery. It is an attempt to address the bone problem at its source rather than compensating for it through exercise and pharmacology. If the skeleton needs directional load to maintain density, the most direct answer is to give it a direction. A rotating structure can do that without requiring the crew to schedule it or the body to actively work for it. The engineering variables that determine whether artificial gravity works for bone are specific. Radius sets the gradient between head and feet. A short-arm centrifuge creates a much steeper gradient than a full radius spinning torus, which matters for fluid distribution and vestibular adaptation. Rotation rate determines how quickly the Coriolis effect becomes disorienting. Head movements in a rotating frame create illusory sensations that can cause nausea and impair coordination. The combination of radius and rotation rate that produces adequate floor-level gravity while keeping Coriolis effects tolerable has not been definitively established for long-duration human exposure. Short-arm centrifuge studies on Earth have tested brief intermittent artificial gravity, a crew member spending 30 minutes per day on a centrifuge rather than living inside a rotating habitat. Results are promising but not conclusive. Bone-specific outcomes from this approach require longer study periods and larger subject samples than current evidence provides. Intermittent artificial gravity might be enough. It might preserve density while avoiding the structural and operational cost of a fully spinning spacecraft. That question is one of the more important open ones in the field. The structural cost of a rotating habitat is real, regardless of the biology. A spinning module requires a mechanism to transfer docked spacecraft without transmitting spin. The docking interface has to manage the angular momentum difference. The internal volume of the rotating section has to accommodate the crew's daily activities in a space where down changes with distance from the axis. Mass, power for the rotation mechanism, and engineering complexity all add to a mission budget that is already constrained. Continuous artificial gravity, a whole spacecraft that rotates throughout transit, is a larger commitment. The vehicle becomes harder to build, harder to dock, harder to operate during emergencies, and heavier to launch. It may also create a bone environment that is measurably better than the current exercise-only approach. Whether that biological benefit justifies the engineering cost is the artificial gravity bargain. It has not yet been made because the data needed to evaluate it, long-duration human bone outcomes under artificial gravity, does not yet exist at the scale required to inform a spacecraft design decision. The rotation rate debate in artificial gravity design centers on two competing concerns. Low rotation rates produce less Coriolis effect and are more comfortable for crew members, but lower rotation rates require larger radii to achieve the same floor-level gravitational force. The centripetal acceleration equation relates force, radius, and rotation rate such that halving the rate requires quadrupling the radius for the same gravity level. A spacecraft design that uses a low rotation rate to minimize Coriolis discomfort, therefore, requires a much larger and more massive structure than one that accepts higher rotation rates. NASA and ESA researchers have proposed various crew tolerance thresholds for rotation rates. Earlier studies suggested that crews could adapt to rotation rates up to about 2 revolutions per minute. More recent work has pushed that threshold higher in some subjects with adaptation and training. The variable of individual adaptation matters because some crew members may tolerate higher spin rates while others experience persistent nausea at lower ones. A vehicle designed for a specific rotation rate is designed for the tolerance distribution of the crew who will fly in it. The on-off question is also open. A vehicle that rotates continuously for the entire transit provides constant artificial gravity loading. A vehicle designed with a centrifuge section that can be activated for 2 hours per day, while the rest of the spacecraft remains non-rotating, could provide intermittent loading while avoiding the operational complications of full-time rotation. Whether 2 hours per day under artificial gravity loads bones sufficiently to prevent the losses seen in current missions is exactly the question that short-arm centrifuge research is trying to answer. The answer would determine whether the large-scale engineering commitment of a continuously rotating spacecraft is actually necessary. The economics of artificial gravity are not only structural. A rotating spacecraft changes how crew members experience their living environment. Directions become meaningful. Down is always toward the outer wall. Activity planning has to account for the difference between living near the rotation axis, where gravity is weak, and near the outer rim, where it is stronger. Food preparation, hygiene, and sleep all take place in a gravitational gradient rather than uniform microgravity. These are not insurmountable problems, but they require design solutions that current spacecraft do not need. The engineering cost of artificial gravity includes not just structure and mass, but the cognitive and operational redesign of how a crew lives and works across a multi-year transit. The question of what level of artificial gravity is actually needed for bone also depends on the answer to the partial gravity threshold question. If bone can be maintained at 0.38 g, if Mars gravity turns out to be above the minimum effective threshold, then a spacecraft that provides 0.38 g during transit might be sufficient. That is a much lighter and simpler design target than one that provides full 1 g. A tether-connected spacecraft spinning to produce 0.38 g floor-level acceleration would require a shorter radius than one targeting 1G, which is the difference between an engineering challenge and an engineering impossibility with current propulsion. The threshold research and the artificial gravity design research are linked. Knowing where the threshold is determines how hard the artificial gravity engineering has to work. Hybrid approaches may offer practical solutions that fully rotating or fully stationary spacecraft do not. A transit vehicle could maintain a non-rotating living environment with standard exercise hardware for most of the mission, while crew members use an onboard centrifuge for prescribed daily sessions at higher G levels targeting specific bone loading. This intermittent approach avoids the full structural commitment of a rotating habitat while providing bone loading that exceeds what exercise alone achieves. Whether this hybrid approach provides adequate bone protection at mission-relevant durations is, again, an empirical question that current short-arm centrifuge research is approaching but has not yet answered at the required scale. The research agenda and the engineering design space are running in parallel, and neither is ahead of the other. Calcium leaves bone in measurable quantities during spaceflight and shows up in urine. That calcium has to go somewhere, and where it goes causes secondary problems. Elevated urinary calcium raises kidney stone risk, a risk already documented in astronauts, and one that becomes particularly dangerous without rapid surgical access. The spine and hip are losing density, and the body is shedding the released minerals through the kidneys. Bone loss is not a private skeletal event. It is a change in the body's mineral chemistry, with consequences that extend past orthopedics. That connection is why bone loss cannot be managed as a single system problem. The calcium being released from the femoral neck and lumbar vertebrae moves through the bloodstream and the kidneys. Urinary calcium rises. The risk of kidney stones rises with it. Crew members on ISS have formed kidney stones during and after missions, and the connection to elevated urinary calcium is documented. A kidney stone in orbit is a serious medical event. A kidney stone on a surface EVA far from the vehicle is worse. Muscle loss and bone loss run on parallel tracks during microgravity exposure. Both respond to reduced mechanical demand. The muscles that stabilize the spine, the erector spinae and multifidus, lose mass and strength during spaceflight, and their capacity to protect the vertebral column from compressive and shear forces is reduced. Bone loss in the lumbar spine and weakened spinal musculature form a combination that increases the risk of vertebral injury during high-force events. The skeleton and the muscles around it need each other, and they degrade together. Balance and proprioception also change during spaceflight. The vestibular system adapts to microgravity over the first days of a mission, and it begins to adapt again at landing. During that readaptation period, crew members are more vulnerable to falls. A fall shortly after landing, with reduced bone density and diminished spinal muscle protection, is the condition that concentrates multiple risk factors at the same moment. Post-landing protocols include monitored recovery for precisely this reason. The transition back to gravity is a high-risk window. The immune-bone connection adds another layer. Inflammatory cytokines that increase during spaceflight can stimulate osteoclast activity independently of mechanical unloading. This means that the bone loss pathway is not driven only by absent load. Immune signaling may amplify it. Crew members experiencing elevated inflammatory markers lose bone through an additional channel. Countermeasures that address only mechanical stimulation may miss this component of the problem. From a mission design perspective, these connections mean that protecting bone also protects multiple downstream systems: kidneys, musculature, balance, immune regulation. The case for investing in bone countermeasures is not just about the hip. It is about the whole system that the hip is part of, and what happens to that system when one component degrades more than the others. The cardiovascular system adds its own parallel track. Fluid shifts in microgravity move blood volume toward the upper body. The heart responds by reducing its workload, and over months, cardiac muscle atrophies. Orthostatic intolerance on return, the body's difficulty maintaining blood pressure when standing up, is one of the most consistently documented post-mission challenges. A crew member who has lost bone density, muscle mass, and cardiovascular conditioning simultaneously is facing a stacked physiological deficit at exactly the moment when the mission requires physical performance. Pain in the spine is a documented microgravity phenomenon with a bone connection. The intervertebral discs absorb fluid and expand slightly in microgravity without the compression of gravitational load. This produces temporary increases in crew member height and also back pain as the spine elongates beyond its normal range. The expanded discs return to normal dimensions over weeks after return to gravity, but the changed spine geometry during flight alters how loads are distributed through the vertebral column during exercise. This may affect which regions of the spine experience the most stress during arid workouts, and therefore which regions most benefit from the countermeasure. The visual and intracranial pressure changes that affect some long-duration crew members also have indirect relevance to the bone question. Spaceflight-associated neuro-ocular syndrome, which includes changes in visual acuity, optic disc swelling, and intracranial pressure, is linked to the same cephalid fluid shifts that occur in microgravity. Some researchers have proposed connections between fluid management, bone metabolism, and intracranial pressure pathways. These connections are not yet clearly established, but they illustrate how far the physiological consequences of microgravity reach from what might initially seem like a local skeletal problem. The operational picture that emerges from these systemic effects is not one of isolated organ degradation, but of an interconnected stress response that the entire body runs in microgravity. Bone, muscle, cardiovascular, vestibular, and neuroocular systems all respond to the same fundamental absence, a planet beneath the crew. Countermeasures that address one system in isolation may protect it while leaving others exposed. The mission physiology problem is not bone loss, it is the whole body response to an environment the body did not evolve for. Radiation exposure adds a further complication to the bone picture. The deep space radiation environment includes galactic cosmic rays and solar particle events that can damage DNA in bone cells. Radiation damage to osteoprogenitor cells, the stem cells from which osteoblasts develop, can reduce the pool of cells available for bone formation. Studies in irradiated animal models show that high-dose radiation can impair bone formation and reduce density. For human deep space missions, the combined effect of radiation and microgravity on bone may be worse than either factor alone. The interaction between these two stresses is not well characterized in humans, and mission radiation shielding design has implications for bone health that go beyond the more commonly discussed cancer risk. Circadian disruption during spaceflight also touches bone metabolism. Bone remodeling has circadian rhythms. Bone resorption peaks at night in humans under Earth conditions, while formation is relatively steady. These rhythms are synchronized by light-dark cycles and the sleep-wake cycle. In orbit, crews experience 16 sunrises per day, and light exposure through station windows is managed but differs from natural daylight cycles. Disrupted circadian rhythms alter the timing of cortisol release, which influences osteoclast activity. Crew members with severely disrupted sleep or circadian dysregulation may have altered bone remodeling patterns independent of their exercise and nutrition countermeasures. Sleep quality monitoring is part of astronaut health tracking in part because of these downstream physiological connections. The connective tissue system beyond bone also degrades under microgravity, with consequences for joint stability and injury risk. Tendons and ligaments experience reduced mechanical loading in weightlessness and lose some of their tensile properties over time. When full loading returns at landing, the joints that these structures protect are at elevated injury risk. The combination of reduced bone density, weaker periarticular muscles, loosened connective tissue, and impaired balance creates a joint vulnerability picture at landing that extends beyond fracture risk to sprains, dislocations, and ligament tears. Comprehensive mission physiology has to account for the whole musculoskeletal system, not only the skeletal component in isolation. The integrated picture from these systemic effects changes how countermeasure infrastructure has to be evaluated. A program that asks only, "Does this protect bone density?" is asking the wrong question. The more useful question is whether the program as a whole leaves the crew capable of full operational function at the moment the mission demands it. Bone density is one component of that capability. Muscle mass, cardiovascular readiness, vestibular stability, and connective tissue integrity are the others. A protocol that protects bone while allowing the others to degrade further from inadequate attention is not a complete solution. Mission physiology programs have been moving toward this integrated framing, but the research and operational design of each system still often runs in parallel rather than together. A returning crew member steps off the plane and walks under full Earth gravity for the first time in 6 months. The skeleton is immediately loaded. Force comes back through the hips and spine. The remodeling balance starts to shift. In the weeks following, DEXA scans track what happens. Some individuals regain most of their lost density within months. Others show partial recovery that stalls before returning to baseline. The bone that was lost was not simply paused, it was resorbed, and the structural microarchitecture that supported it was altered. Reloading the skeleton begins the rebuilding process, but reloading is not the same as restoration. The question is how much of the original structure comes back, how quickly, and whether the answer changes with longer missions. Recovery has the same problem as the mission itself. It runs on a timeline the body controls, not the schedule. A crew member can be back under full Earth gravity, while the bone that was lost is still being rebuilt. The remodeling balance reverses direction when loading returns, but the cellular processes that deposit new matrix operate at the same pace they always have. Weeks become months. For some individuals in some regions, the recovery curve flattens before reaching pre-mission values. The trabecular microarchitecture is the part of the recovery story that density measurements alone cannot tell. Bone resorption during spaceflight removes mineral content and the structural lattice that mineral content supports. New bone deposition after landing rebuilds density, but the pattern and distribution of new trabecular struts may differ from the original. The total bone volume can recover while the internal architecture remains altered. Whether those architectural differences affect practical strength, the ability to absorb impact without fracture, is a question that requires imaging beyond standard DEXA and that has not been fully answered for all mission durations. Fracture risk during the post-landing period is higher than it appears from aggregate density numbers. Returning crew members are weaker than baseline, their balance is disrupted by vestibular readaptation, and their muscles have lost mass. The combination of reduced bone density, impaired balance, and weakened periarticular musculature produces a fall risk profile similar to the one seen in elderly patients following hip fracture. This is managed on Earth by careful supervised rehabilitation, and crew members receive that supervision. The concern is whether a Mars mission crew would have equivalent support, or whether the post-landing period on a distant surface would require physical performance before the body has had time to recover. The recovery timeline also informs how to think about a return mission. A crew that lands on Mars and then faces a second transit home carries whatever deficit the surface stay allowed them to recover or add to. The full round-trip biology of a Mars mission is not a series of separate exposure windows. It is one long arc of loading, unloading, partial reloading, unloading again, and return. And the cumulative effect on the skeleton of that entire arc has not been modeled in humans at scale. The lesson from post-mission data is not that recovery is impossible. Most crew members from station-length missions recover substantially over 6 to 12 months of Earth living. The lesson is that recovery is not guaranteed to be complete, that the timeline is individual and slow, and that for missions longer than those currently flown, the starting deficit before recovery begins may be larger than any returning crew has yet had to work back from. Rehabilitation protocols for returning crew members have become more sophisticated over the decades. The early space program treated astronaut recovery as an informal return to normal activity. Current ISS crew members begin a structured rehabilitation program immediately after landing, with supervised physical therapy targeting the systems most affected by microgravity exposure. The program runs for weeks to months, with regular assessment of bone density, muscle strength, balance, and cardiovascular fitness. This investment in recovery is itself evidence of how seriously post-mission deficits are taken. The rehabilitation data provides a window into which countermeasure approaches during flight are most effective. Crew members who maintained muscle mass and bone density better during the mission typically recover faster after it. The in-flight protocol and the post-flight recovery are connected through the same biology. Better protection during exposure leads to smaller deficits, and smaller deficits recover faster. This feedback relationship justifies the time and mass investment in exercise infrastructure, not just as prevention, but as reduction of the post-mission rehabilitation burden. One gap in the recovery picture is the absence of long-duration return data. No human being has returned from a multi-year microgravity mission and undergone systematic bone recovery assessment across years. The closest analogy is bed rest recovery studies, which show that recovery from long immobilization is slower and less complete than recovery from short immobilization. If that pattern holds for spaceflight, and there is no strong biological reason to expect it would not, then a crew returning from a Mars mission faces a longer, harder recovery than any ISS return crew has yet experienced. The career implication of repeated missions matters too. A crew member who flies 3 ISS missions before a Mars assignment has accumulated multiple cycles of bone loss and recovery. Each recovery may be near complete, but the cumulative structural history of the bone differs from someone who has lived under Earth gravity continuously. Whether repeated spaceflight produces accelerated age-related bone loss in the years after a career ends is a question that is currently being tracked in former astronaut health studies. The answers will inform how future programs think about mission frequency and crew health across career timescales, not just single mission timescales. The bone at landing is not simply the bone at launch with a lower number on the scan. It is bone that underwent a different remodeling history, removed by osteoclasts working in a low-signal environment, then partially rebuilt by osteoblasts refilling under conditions that finally included load again. The new material registers on DEXA, but whether its stiffness, toughness, and resistance to crack propagation match the original is a harder question than density measurement can answer. Nano-indentation studies of bone from spaceflight analog models suggest the material properties of newly deposited bone may differ subtly from pre-flight bone in stiffness, toughness, and resistance to crack propagation. Whether those differences matter for fracture risk under the specific forces generated by surface operations is still being investigated, and answering that question requires imaging and mechanical testing that goes beyond what DEXA alone can provide. The question of what constitutes an adequate recovery baseline before a subsequent mission is unresolved. Current practice for ISS crew members returning to flight involves clearance through medical assessment after an appropriate recovery period. The criteria for clearance are based on available data from ISS mission durations. For a crew member returning from a Mars mission who might face assignment to a second deep space mission years later, the recovery assessment would need to establish not just that density has returned to a normal clinical range, but that the structural quality and mechanical properties of the bone are adequate for another demanding mission. The standards for that assessment do not yet exist in the required detail. Bone age, the structural and biological age of bone tissue as distinct from chronological age, is a concept with emerging relevance to spaceflight medicine. An astronaut who has experienced multiple cycles of accelerated remodeling may have bone whose structural history resembles older bone even if their chronological age is younger. The long-term health implications of this accelerated bone age, including implications for fracture risk and mobility later in life, are subjects of active longitudinal follow-up in astronaut health cohorts. The program of post-career health monitoring that NASA conducts for former crew members is designed in part to capture these long-term effects. Oleg Kononenko landed in September 2024 after 374 continuous days in orbit. His bones had been under active countermeasure management that entire time. His recovery took months. That mission is the longest single-duration flight in the record, and it covers less than half of a round-trip Mars timeline under optimistic propulsion assumptions. No human being has accumulated the full 900-plus days a Mars round trip would require. The protocols built from station-length stays are the best available baseline, but they are not evidence for permanence. Duration is not background detail. It is the variable that most changes what the skeleton faces. Short exposure can teach the wrong lesson if it is treated as proof of permanence. A body can tolerate a condition for a while without proving that the condition is safe as a permanent state. The difference between a 6-month mission and a 3-year mission is not simply 5 additional 6-month segments. The biology changes as duration extends, and the extrapolation from short mission data to long mission prediction carries significant uncertainty. ISS mission data and the protocols derived from it were built through decades of iterative refinement across progressively longer missions. They represent genuine progress, but the protocols have not been tested at the duration they would need to protect. The gap between the longest recorded flight and the full round-trip Mars timeline is not a technical refinement problem. It is an extrapolation into conditions that have never been measured. One specific concern with longer durations is whether the rate of bone loss changes over time. Early mission data from ISS suggests that loss rates may not remain constant. Some crew members show faster early loss that slows, while others show progressive loss without a plateau. If loss rates can accelerate with cumulative exposure, a longer mission may not produce proportionally more loss than a shorter one, or it may produce significantly more. The data to resolve this does not yet extend to mission durations relevant for deep space exploration. The timeline problem also applies to countermeasure development. The exercise systems and protocols in use on ISS took years to develop and validate. A Mars mission that identifies a problem with bone health mid-transit cannot rely on a rapid upgrade to its exercise infrastructure. Whatever countermeasures the mission launches with are the countermeasures it has for the full duration. This means the standard for what counts as adequate protection has to be set before departure, with enough conservatism to account for the full possible duration, not just the nominal timeline. Settlement planning introduces a further dimension. A permanent human presence on the Moon or Mars is not a question of single missions. It is a question of what physiological systems can sustain indefinitely under conditions that differ from Earth. The bone data from mission-length stays is a starting point for understanding that question, not an answer to it. Whether humans can live for years under lunar or Martian gravity without progressive skeletal compromise is something the bone data collected from short missions cannot tell. The specific physiological question for settlements is not just whether bone density can be maintained, it is whether the full range of physical capability required for life and work on another world, lifting, carrying, falling safely, recovering from injury, performing repeated physical labor, can be preserved indefinitely under partial gravity with reasonable countermeasures. A settlement that requires every resident to spend 2 hours per day exercising just to maintain basic physical safety is viable, but the time and energy cost of that requirement shapes every aspect of settlement design and productivity. Children born on Mars or raised there from infancy present a further question that has no existing data at all. Bone development in children and adolescents requires mechanical loading to drive the skeletal growth and density accumulation that establishes peak bone mass. A human skeleton that develops under 38% gravity rather than Earth normal gravity may achieve different structural outcomes than one that develops under Earth conditions. Whether Mars-born humans would have adequate bone strength for Earth-level activities, and whether that matters for a population planning to live on Mars permanently, is a question that settlement medicine will eventually have to address. Human aging provides a useful frame for setting scale. Women lose bone density during menopause at rates of 1 to 2% per year in the hip. Microgravity exposure can match or exceed that rate per month. Osteoporosis in older adults causes fractures, loss of mobility and reduced independence, and those consequences map directly onto mission-critical concerns about crew performance. Space medicine has borrowed extensively from osteoporosis research, and that cross-disciplinary connection has accelerated the countermeasure toolkit. It has also confirmed that spaceflight bone loss rates are serious by any clinical standard, not only by spaceflight-specific ones. The timeline of space exploration that is currently planned places humans on the Moon before the end of the 2020s, and potentially on Mars before 2040. The bone physiology research that will protect those crews is running in parallel with that mission timeline, not ahead of it. Some of the research questions that matter most for Mars mission crew safety will not be answered before the missions are in planning phases. Mission designers will make decisions about countermeasure systems, habitat design, and crew selection based on the best available evidence at the time, knowing that the evidence is incomplete and that the missions themselves will generate much of the data that future missions will depend on. The institutional response to the bone loss problem has evolved significantly since the early space program. Skylab missions in the 1970s documented bone loss that alarmed researchers but was treated with limited follow-up, as mission constraints made comprehensive monitoring difficult. Soviet and Russian long-duration missions on Mir established that 6-month and 12-month spaceflight was physiologically survivable, but demonstrated the scale of bone and muscle loss under even partially managed conditions. The ISS era introduced systematic pre- and post-mission DEXA scanning, standardized exercise protocols, and ongoing research on interventions. Each generation of missions has produced countermeasures that the next generation builds on. Each generation of missions has generated countermeasures for the next, and a Mars mission will launch with better bone protection infrastructure than any long-duration mission before it. Progress is real, but the fundamental research question has not kept pace with the improving tools. What is the minimum effective load for bone maintenance, and does current ISS-derived practice meet that threshold for missions longer than any currently flown? Better hardware is being built. Validation data for the durations it will face is still being collected. Personnel who will fly on future deep space missions are already in various stages of selection, training, and early assignment. Bone physiology research published in the next decade will directly inform the countermeasure protocols they follow. Scientists doing that research and astronauts who will depend on it are working in overlapping time. A rare connection between laboratory physiology and operational crew safety that makes the urgency of the field concrete rather than abstract. The lesson from every generation of missions is that short-duration optimism becomes long-duration evidence. What looked manageable at 3 months became a serious concern at 6. What looks manageable at 6 months may look different at 2 years. Each time the mission envelope has extended, the physiology response has surprised researchers with the scale of adaptation the body is capable of when given enough time and reason to change. That pattern is the strongest argument for treating the duration gap as a genuine unknown rather than a linear extension of what has already been measured. A rotating habitat needs a spin rate. An exercise protocol needs a load target. A surface mission habitat needs a schedule for daily exercise. Each of these requires a number, the minimum gravitational load that preserves bone density in the hip and lumbar spine over months of exposure. That number does not exist in human data. Gravity clearly helps bone. More load produces more bone, and that relationship is consistent across every study. What has not been established is the threshold. How much gravitational load, applied how often, for how long per day, is the minimum that keeps the structures intact for mission-critical physical work. Ground-based bed rest studies and short-arm centrifuge experiments have explored pieces of this. Rodent studies aboard the Space Shuttle and ISS have added data points. But the missing human threshold drives uncertainty into every design decision downstream of it. The missing threshold is not a philosophical detail. Every hardware specification, every exercise time allocation, every habitat layout decision downstream of it carries that uncertainty inside it. An artificial gravity rotation rate that was chosen without knowing the minimum effective dose of gravity for bone may produce either more than the skeleton needs or less than it requires. A surface habitat designed for 2 hours of daily exercise may be adequate or insufficient. The threshold determines which is true, and it has not been established. Bone research has approached the threshold question from multiple directions. Bed rest studies replicate the unloading condition by having subjects lie horizontal for weeks or months, removing gravitational loading from weight-bearing regions. These studies have produced density loss rates that parallel spaceflight data and have tested various interventions. But bed rest is not microgravity. The two conditions differ in fluid distribution, cardiovascular effects, and spine loading patterns. Bed rest data informs the problem without directly answering it. Rodent centrifuge studies have tested hypergravity, loading above Earth normal, and have mapped the dose-response relationship between gravitational load and bone density in small mammals. The data confirms that more load produces more bone. It does not translate directly to the minimum required for humans, because rodent bone biology differs from human bone biology in ways relevant to this question. Partial gravity rodent studies, including experiments flown on the Space Shuttle and planned for future platforms, are attempting to fill the sub-1 G section of the dose-response curve in living organisms. Each experiment produces data. None has yet produced a human-applicable threshold for the specific regions, femoral neck, lumbar spine, that matter most for mission operational capacity. What mission design has to do in the absence of the threshold is proceed with conservatism. The current exercise protocols are set to the highest level the available hardware and mission schedule can support. Countermeasure research continues in parallel. Monitoring provides feedback that can identify when the protocol is and is not working for individual crew members. The approach is empirical. Measure, adjust, measure again. It is not the same as knowing the answer, but it is more honest than designing a mission around a threshold value that does not yet exist in human data. Animal models have allowed researchers to test partial gravity by using various incline angles in bed rest analogues and by flying rodents in centrifuges aboard spacecraft. These experiments show that bone loss rates decrease as load increases, and that at some load level the loss stops. The critical complication is allometric scaling. The relationship between body size, bone geometry, and load tolerance differs between rats and humans in ways that make direct threshold translation unreliable. A rat maintaining bone at 0.38 G may not predict a human maintaining bone at 0.38 G. The most direct path to answering the threshold question for humans would be placing human subjects under precisely controlled partial gravity for extended periods and measuring bone outcomes. That experiment cannot currently be conducted on Earth at the necessary scale and duration. The closest approximations, brief centrifuge sessions, tilt table studies, underwater simulations, all differ from the real condition in important ways. The threshold will ultimately be established by the missions themselves, measured from the crew members who live under lunar and Martian gravity for months and years and return for assessment. The first crewed Mars mission will be, in this respect, also the largest and most consequential bone physiology experiment in history. The design of that experiment, which is also a mission, matters for the quality of the science it generates. Rigorous pre-mission baseline assessments, standardized in mission monitoring protocols, consistent post-mission follow-up, and shared data across programs and nations would allow the first Mars mission bone data to advance the field rather than simply document the outcome for that particular crew. The science value of the mission's physiological data is proportional to how well the measurement and documentation protocols are designed before launch. Animal models will continue to inform the field, while human data remains limited. The Space Centrifuge Research Facility planned for future station configurations would allow rodent experiments in controlled partial gravity environments over extended periods. These experiments could test whether 0.38 G is above or below the minimum effective threshold for rat bone, and whether pharmacological interventions modify that threshold. The translation to human biology is imperfect, but controlled partial gravity animal studies could establish the mechanistic framework that human data would then test at scale. The relationship between exercise type, gravity level, and bone outcome is likely interactive in ways that current protocols do not fully capture. A person exercising under 0.38 g may generate different loading patterns than a person exercising under 1 g or in microgravity. The same squat or deadlift exercise produces different forces on the femoral neck depending on the background gravitational field. This means that exercise prescriptions optimized for ISS microgravity may not be optimally designed for Mars surface use. Surface-specific exercise protocols that account for the actual gravitational environment, including how it affects ground reaction forces, joint loading, and spinal compression, would need to be developed and tested. That work has begun in simulation, but the real-world data to validate it will only come from humans exercising on Mars. Impact loading is a different category from resistance loading, and the two act on bone through different mechanisms. Resistance exercise generates compressive force through muscle contraction. Impact exercise, running, jumping, drop landings, generates transient high-magnitude strain spikes that are particularly effective at driving bone formation through the mechanosensory pathway. On Earth, walking and running produce impact loads through the heel strike that travel up the leg and reach the femoral neck and lumbar spine. The absence of this impact loading in microgravity is as significant as the absence of background bodyweight compression. Resistance exercise on the ARED can substitute for compressive load, but does not fully replicate impact loading mechanics. On the Martian surface, walking and running at 0.38 g generate lower ground reaction forces than the same activities on Earth because body weight is lower. The impact spike that drives bone formation under Earth conditions is reduced even if the gravitational field is present. This is a practical reason why returning to Mars, gravity does not automatically restore Earth-equivalent bone loading. The impact stimulus that matters for the femoral neck and lumbar spine is proportional to body weight, and body weight at 0.38 g is 38% of its Earth value. The frequency and magnitude of impact loading that most efficiently drives formation in that environment is another specific, unanswered question in the threshold research space. Wearable vibration devices have been studied as a supplement to both resistance and impact loading for spaceflight bone protection. Low-magnitude, high-frequency mechanical stimulation, delivered through a vibrating platform or wearable device for brief daily sessions, has shown some bone protective effects in ground-based studies of populations at risk for bone loss. The mechanism is distinct from both resistance exercise and impact loading. It appears to act through the fluid dynamics of bone canaliculi, stimulating the osteocyte network at loading magnitudes below those required for conventional exercise. Whether this stimulus level, which is compatible with passive use during other activities, is sufficient to contribute meaningfully to bone protection in spaceflight is under investigation. It is not a replacement for resistance exercise, but as a supplemental tool in a resource-constrained environment. Its potential contribution to the countermeasure toolkit is worth the research investment. The threshold question, ultimately, is a question about biological minimum requirements in an engineering context. Mission designers need numbers they can build to. Biologists need experimental conditions they can control. The two communities are working toward the same answer from different directions. A threshold value for minimum effective gravitational loading of human bone, expressed in terms of G level and daily duration, would allow both communities to make decisions that are currently made under uncertainty. Until that number exists, the threshold debate will continue to be resolved by building more countermeasure capability than the minimum requirement, because the minimum requirement is not known, and the cost of guessing too low is a crew that cannot perform the mission it launched to complete. Return to the crew member drifting through the module at the start. The image has not changed. The hand still finds the rail. The feet still hover. The hips and spine still look unburdened. What has changed is the understanding of what that ease costs. Zero gravity does not fracture bone. It does something harder to see. It removes the mechanical argument for maintaining density in regions the body no longer needs to load. The skeleton is not failing. It is being logical. The problem is that the mission will eventually need it to be strong again. The final issue is confidence. Spaceflight requires it. Missions depend on decisions made under time pressure, in situations that allow no delay for uncertainty. That operational requirement for confidence can run ahead of the physiological evidence base. The more ambitious the destination, the more important it becomes to hold a clear distinction between what is known about bone physiology in space and what is assumed. What is known: density loss in weight-bearing regions during standard station missions is measurable and consistent. Countermeasures reduce but do not eliminate it. Individual variation is significant and not yet predictable. Recovery after return to Earth is substantial but not guaranteed to be complete. Density loss correlates with fracture risk factors used in clinical medicine. Post-mission bone data from returning crew shows the system is trackable and responsive to intervention. What is assumed that 6-month mission protocols scale to much longer durations, that the density deficits observed on ISS translate linearly to Mars mission timelines, that partial gravity on the Moon and Mars provides meaningful protection in amounts sufficient for long-term habitation without the same level of countermeasure infrastructure needed in orbit. Those assumptions may prove correct. The research evidence that would confirm or refute them does not yet exist at the scale and duration required. Missions to the Moon and Mars will generate that evidence as they unfold, but the missions will also require physical human performance before the evidence is complete. The crew will step onto surfaces before anyone knows for certain whether the remodeling balance they carried through transit left them with adequate reserve for what the surface demands. That opening image has not changed. The hand still finds the rail, feet still hover. Nothing about the posture suggests a problem. What has changed is the understanding behind the image. It is accurate and incomplete at the same time. Nothing is failing. No immediate danger exists. What is happening, slowly and without announcement, is that the skeleton is reading its environment and drawing a conclusion about how much strength the world it lives in actually requires. And the world it will eventually have to work in requires considerably more. What zero gravity actually destroys is not bone in the dramatic sense. It destroys the assumption that the body will be the same organism at the end of the mission as it was at launch. Mission planning depends on that assumption. Vehicle systems hold their specifications, navigation holds its calibrations, and crew capability holds its baseline. Unlike hardware, which is engineered to maintain specifications in controlled conditions, the body's physiological systems actively adapt to the mission environment, and the direction of that adaptation for bone is not toward greater readiness, it is toward a lighter world. Exploration history is full of examples where human physical capability turned out to be the limiting factor, not the technology, not the supplies, not the navigation. Scurvy ended voyages, cold ended expeditions. What failed was the body, and the missions that carried it did not fully account for what the body actually required. Spaceflight bone loss belongs in this history. Deep space exploration has identified it, studied it, and partially managed it, and it still lacks a complete solution. The solutions being developed are real. Exercise hardware has improved substantially since the first space station missions. Bisphosphonate protocols have been tested. Nutritional monitoring has grown more precise. Artificial gravity research has moved from theoretical to experimental. Progress is real and ongoing. What matters is that each improvement stays connected to actual physiological requirements, rather than to engineering convenience. A bone countermeasure that fits the spacecraft budget but does not adequately protect the femoral neck is a countermeasure in name only. The body the crew brings to the mission is the same body it was built with, shaped by millions of years of evolution under Earth's gravity, calibrated by decades of living, structured by the forces that Earth asked of it every day. That body is now being asked to function in an environment it did not evolve for durations it has never experienced, towards destinations it has never reached. The bone problem is a specific, measurable consequence of that mismatch. It can be studied, managed, and partially solved. Whether it can be solved fully enough to support indefinite human presence beyond Earth is the open question that sits at the center of every ambitious mission timeline that has yet to be flown. The scientific community studying this question is not pessimistic. DEXA scanning, high-resolution imaging, mechanobiological assays, pharmacological intervention, and improved exercise hardware together represent a dramatic improvement over what the ISS program started with. Each iteration of countermeasure research has reduced the bone loss rates documented in earlier missions. Progress is real, and its direction is toward better protection. What the field asks of mission planners and program designers is honesty about what is currently known and what is assumed. The bone loss problem has been managed successfully enough for station-length missions that it can slide into the background of deep space planning as a solved problem. It is not a solved problem, it is a managed one, and the management strategy has not been validated at the durations and conditions that deep space exploration requires. Treating it as solved would repeat the historical pattern of physiological risks that were assumed manageable until the mission duration or destination exposed the limits of that assumption. The measurement and monitoring infrastructure that exists for ISS crews needs to follow them to wherever the mission goes. Pre-mission baseline scans, in-mission monitoring where technology allows, post-mission follow-up, and longitudinal career tracking are the scaffolding around which countermeasure evidence accumulates. That scaffolding is more valuable the more consistently it is maintained. A Mars mission whose crew returns without systematic bone density assessment has missed the most important data collection opportunity of the era. The missions themselves have to be designed as learning instruments, not just transportation events. The bone that holds up a crew member at the top of the first ladder on Mars, the one whose foot contacts the surface first, whose hip absorbs the step under 38% gravity after months of transit, is the product of everything that happened to that skeleton from birth to that moment. It is the product of childhood calcium intake and adolescent physical activity, of adult fitness and mission preparation, of in-flight exercise and pharmacological management, of the quality of the equipment, the discipline of the schedule, and the luck of individual biological response. Every element of that history is traceable back to the same fundamental biological requirement. Bone needs force, and it will negotiate with whatever the world provides to decide how much force it seems worth maintaining the capacity to handle. Return to the crew member drifting through the station module. Nothing about the image has become less calm. The hand still finds the rail, the feet still hover, the body still looks almost effortless. What has changed is what the quiet means. Those hips, that spine, those legs are not passive parts carried through space. They are living tissue, maintained by signals, shaped by force, and trained by the world around them. Zero gravity does not destroy bone like a sudden weapon. It changes the instruction environment around bone. The skeleton keeps remodeling, but the old Earth message grows faint. In the regions that normally carry weight, that missing message shows up as measurable density loss in the hip and lumbar spine, rising fracture risk relative to pre-mission baseline, and a recovery timeline that can extend for months after landing. These are not dramatic events. They are the cumulative outcome of a biological negotiation that ran continuously and silently from launch to return. That is why the answer is neither panic nor comfort. Station crews have learned to fight back with exercise, resistance, scans, nutrition, and careful monitoring. Those countermeasures matter. They make modern missions possible. They also reveal the size of the problem, because a spacecraft has to spend time and machinery replacing what a planet provides without effort. Mars makes the question sharper. A crew does not only have to arrive, they may have to land, stand, carry loads, make repairs, and keep working far from Earth. The skeleton that was quiet during transit becomes part of the survival system on the surface. The Moon and Mars may help. Artificial gravity may help. Drugs and better exercise systems may help. But the honest boundary remains open. How much load is enough? For how long and in what form to keep humans strong away from Earth? The old dream of space travel often begins with distance. How far can the engine go? How much fuel can the vehicle carry? How long can the habitat last? The bone problem adds a quieter question. How much gravity does a human body remember needing? A future ship may solve that question with better exercise systems. It may solve part of it with medicine. It may solve part of it with rotating rooms, surface schedules, or habitats designed around the amount of load the body truly needs. None of those answers is simple, but each one begins from the same recognition. Bone is not baggage. Bone is active mission hardware made by biology. The question is not whether humans are too fragile for space. The record already says otherwise. People adapt, train, and build better machines. That matters, because the bone problem is not a verdict against exploration. It asks for honesty about what a body actually needs. A spacecraft can protect air and temperature, but it must also respect load, strain, recovery, and time. The question becomes more exact and more useful. What does a body require from a world to live there for years, and how carefully must future missions recreate that when the natural world is no longer underneath the crew? Until that question is answered, zero gravity remains more than a beautiful floating scene. It is a test of whether the body that reaches the future can still stand up in it, work there, recover there, and carry enough strength for the long journey home after years away. The tools to answer it exist. The research to validate them is running. The missions that will test them are being planned. And somewhere in a space agency training facility, a crew member is doing the daily exercise that represents the best current answer to a question that science has not yet fully resolved. Putting force back into a body that the mission environment would otherwise quietly convince that less force is what the new world requires. That daily discipline is not proof that the problem is solved. It is proof that the problem is understood well enough to fight back against. The fight continues until the answer is complete.